Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 4, Topic 5. Understanding Series and Parallel Thermal Models in Semiconductor Packaging. Applications, Characteristics, and Trade-offs. Introduction. In the realm of semiconductor packaging, thermal modeling plays a crucial role in understanding heat transfer mechanisms, optimizing thermal management strategies, and ensuring device reliability. Two common approaches to thermal modeling are series and parallel thermal models, each offering distinct advantages and applications. This overview delves into the differentiation between series and parallel thermal models in semiconductor packaging, exploring their characteristics, applications, and trade-offs. Series thermal models. Series thermal models represent the thermal resistances in a semiconductor package as a series of interconnected components, analogous to resistors in an electrical circuit. Each thermal resistance component represents a specific aspect of heat transfer, such as conduction through materials, interface resistance, or convection to the ambient environment. The total thermal resistance in a series model is the sum of individual resistances along the thermal path. Characteristics of series thermal models. Sequential heat flow. In series thermal models, heat flows sequentially through each thermal resistance component, from the heat source to the heat sink or ambient environment. Cumulative resistance. The total thermal resistance in a series model is the sum of individual resistances, reflecting the cumulative effect of each thermal barrier on heat transfer. Simplified representation. Series thermal models provide a simplified representation of heat transfer paths in semiconductor packages, making them suitable for initial thermal analysis and conceptual design. Applications of series thermal models. Conceptual design. Series thermal models are often used in the initial stages of semiconductor package design to assess the overall thermal performance and identify potential thermal bottlenecks. Sensitivity analysis. Series thermal models enable engineers to conduct sensitivity analysis by varying individual thermal resistance components and assessing their impact on overall package temperature. Trade-offs of series thermal models. Simplified representation. While series thermal models offer a simplified representation of heat transfer paths, they may overlook complex interactions between thermal resistance components, leading to inaccuracies in predictions. Limited detail. Series thermal models may lack the level of detail required for accurate thermal analysis in complex semiconductor packages with heterogeneous materials and multiple heat sources. Parallel thermal models. Parallel thermal models represent the thermal resistances in a semiconductor package as parallel paths for heat flow, analogous to branches in an electrical circuit. Each parallel path represents a distinct thermal pathway through which heat can transfer, such as conduction through different materials, multiple heat sources, or alternative cooling mechanisms. The total thermal resistance in a parallel model is determined by the combination of resistances along each path. Characteristics of parallel thermal models. Multiple heat paths. Parallel thermal models account for multiple heat transfer paths within a semiconductor package, allowing for a more comprehensive analysis of thermal behavior. Distributed heat flow. In parallel thermal models, heat flows concurrently along multiple paths, distributing thermal energy more evenly throughout the package. Detailed representation. Parallel thermal models provide a more detailed representation of heat transfer paths, enabling engineers to analyze complex interactions between thermal resistance components. Applications of parallel thermal models. Detailed analysis. Parallel thermal models are particularly useful for detailed thermal analysis of complex semiconductor packages with heterogeneous materials, multiple heat sources, and diverse cooling mechanisms. Optimization. Parallel thermal models facilitate optimization of thermal management strategies by identifying the most effective heat transfer paths and optimizing material selection, package design, and cooling solutions accordingly. Trade-offs of parallel thermal models. Increased complexity. Parallel thermal models are more complex than series models, requiring detailed characterization of individual thermal resistance components and consideration of interactions between parallel paths. Computational intensity. Analyzing parallel thermal models may require more computational resources and time compared to series models, particularly for simulations involving numerous heat transfer paths and complex geometries. Conclusion. Series and parallel thermal models are two fundamental approaches to thermal modeling in semiconductor packaging, each offering unique advantages and trade-offs.
Series models provide a simplified representation of heat transfer paths and are suitable for conceptual design and sensitivity analysis. In contrast, parallel models offer a more detailed analysis of complex thermal behavior and are valuable for optimizing thermal management strategies in heterogeneous semiconductor packages. By understanding the characteristics, applications, and trade-offs of series and parallel thermal models, engineers can effectively analyze and optimize thermal performance in semiconductor packaging, ensuring the reliability and performance of electronic devices in diverse applications. Thanks for watching.
Please like, share, and subscribe.